Okay, so in this module, which is basically a tutorial, we are continuing discussing of this Turing pattern hands-on Fitzhugh Nagumo, where we try to at least get some understanding of what is happening. You saw the patterns, we put in those parameters, you do get those patterns, but how and why is also an important question. So, in one of the previous tutorials, we discussed when we are just doing the diffusion equation, right? I mean, where the R1 and R2 terms had been switched off. Now, suppose here we switch off the diffusive terms and just look at the so-called R1 and R2 when they are finite values. Okay, so this is one thing that I'm going to do. The other thing that I'm going to do is have a faster movie speed. I'll go back to point one. There are 40 snapshots in this. And wait, I'm also going to take this color map, right, and replace it to in domains B, because so what's the difference in domains B? It's basically uploading mechanically initialized, which has essentially the densities at different lattice points, the density of B. And what I'm going to do is add this particular color map, going to ensure okay, C-axis has a slightly different range here. I'll keep it from minus zero point 0.5 to plus zero point 0.5. We can change that also later. And pause is 0 0.1, 61 to 61 is the lattice size. I think I'm doing fine. Okay. So now just to have a look, now suppose alpha equal to 0 0.005, beta equal to 10. So you have only the Fitzhugh-Nagumo terms without the diffusive term. I mean, diffusive terms have been switched off, not explicitly in the code, but by uh, basically putting the diffusion constant uh, values to be equal to 0, right? Dt is 0.002, dx dy is remains 1. And what do you expect? Now we already analyzed that when alpha has some positive value, right, then basically a plus alpha will be equal to a cube, and that is going to be the solution, right? That is the steady state solution. In here, you won't get density inhomogeneities. Now let's see. So you're starting from different. So the initialization at each lattice point is some value between minus zero point 0.5 and plus zero point 0.5 by virtue of this step and this step where I'm calling random numbers, right? I'm calling random numbers between 0 and 1 for temp A and temp B. And then I'm shifting these values by minus zero point 0.5 so that you have random numbers between minus zero point 0.5 and plus zero point 0.5. And ideally, you would expect it to yeah, go to, so the steady state at each lattice point, it should go in absence of the diffusion terms to a fixed point, right? And does it do so? So what we're going to do is, of course, compile, run, right? And then plot, right? The domains. So at each lattice point, the values are evolving and the value which is evolved to is this pink color. So somewhere value between zero point 0.1 and zero point 0.2 is what my expectation is. And if you see, uh, it was the fixed point was supposed to be cube root of alpha. Alpha has been chosen to be 0.005, and cube root of alpha to the power 0.3333 is 0.171, right? So that should be the values of a all over. And I think, I mean, I can't tell the exact color, but I think I would expect this to match with around 0.171. We can also look up the values here. 0. Initialize. Uh, yeah. So here you see most of them have values very close to 0.171, and somewhere some differences, but maybe if you allow it to run a bit more, it will basically reach stable point at each point. What about B? B, I mean, from the analysis that we did, is should be very similar. It should be identical to the values of A when diffusion constant is not there. I mean, diffusion terms are not there. Let's just check. So I'll switch this off, and domains B. It's again evolving. At different points, you had different values, and now after evolving, you're seeing that it's reaching almost the same color. Some color very close here, so this should again be 0.17. So this at least follows our intuition. Now, what would happen if we had changed the value of, say, beta? Okay. So beta, if you remember, is del B del T is proportional to beta alpha minus uh, B. So if I change to 1, okay, and run it, does it move faster? I don't think so from these numbers, but let's have a visualization. The value of beta is unlikely, at least visually, I can't figure out any significant differences. Playing with these four parameters, there are interesting. There are, I think, more variations if you look at it, right? So after it has reached close to the fixed point, it is decaying more slowly. Hence, it hasn't fully equilibrated. Yes, and whatever you are seeing visually, here you have more variations from 1.15 and 0.18 and so on and so forth. So there are variations compared to uh, previous values. Okay. Now, okay. Okay. Now, if we went to choose alpha to be minus, right? What would happen? And the other thing I want to do is basically suppose we start out all so that all the lattice sites have random numbers between 0 and 1. Okay, so the shifting of between minus zero point 0.5 and plus zero point 0.5, that is switched off. Then I compile again and run it again. So I'm going to kill this. and domains. So it evolved. Again, you see some spots and to a value which seems to have gone to minus 0.17 is what my guess would be. Right? Now, one has to do a proper analysis of why that happens. But okay, so that's what happens. And okay, now if I choose a alpha value, right, uh, greater than 1, then let's see what happens. If then the fixed point would be greater than point would be greater than 1. I have to change this range. So say from 0 to 2, right? Because I expect, uh, okay, so now let me change the value of alpha to 1.05. And let me change the value of beta back to 10 so that it evolves faster. That's the logic, and diffusion constant has still been kept. Different, I mean, yeah. So you see the diffusion constant is equal to 0, and if I run it, oh yeah, so this has a huge value. Okay, this is 3659. So there are 3600 lattice points, and so basically it must have gone. It went really fast, it seems. It really quickly evolved to some value here. See this color. Now, if I had decreased the beta, then let's see what happens. So I'm trying to get an understanding of what is happening even without the diffusive term, just uh, what we learned from linear stability. And you see that there's no variation, space dependent variation in the density of A, and similarly density of B. Uh, so there's no so basically so at each point it is going to the same value. These are not so called Turing patterns, right? Because Turing patterns have these variation intensities at different points in space. Sometimes you get spirals also, but that's a entirely different ball game. So let's see what happens here. All that I did is decrease beta, and oh, it again went very fast. So I think you're going to get the same plot as before. But now if I switched this on, okay, so I think it is because of the presence of alpha, it will. So now we have initialization between minus zero point 0.5 and plus zero point 0.5 just as before. But my guess is it will still reach the same fixed point rather fast. Took a bit more time, but it's always reaching the same fixed point and rather fast is all that I can get here just to visualize. So again, you have this point, I mean, uniform density, it just reaches its stable fixed point, each lattice point, and each lattice point has the value, some number just above 1 corresponding to this color, right? I mean, this color. Now, okay, so that's what's happening with just the Fitzhugh Nagumo terms without the diffusive equation. But if now I switch on diffusion constant, this this has to be much larger, 100. uh, I'm not going beyond 100, and alpha I shall decrease this range. The initialization over different points in the lattice is between minus zero point 0.1 and point. Okay, I think we already did this, but let's repeat it. So you distinctly get density inhomogeneities as you see, right? So some points have value 0, some other points have some value 1. It's looking different because I changed the range of the interaction, right? Sorry, of the color axis. So some points have this value, some number close to 1, others have black. What? And you see there's this huge lobe here, there's this huge lobe here, this huge lobe here. What does domains B do? Did I change the value of domains B also? So domains domains B, and its range is, I should change it to 0 and say 2 to have parity, right? And I think Paul's color is 1. Okay, it's primarily 0. So remember, B is an inhibitor. B is an inhibitor, so its value is close to 0. But remember, del B del T depends upon the difference in values of um, A and B. And if you remember, though the values are close to 0, you can see a lobe here, a lobe here, a lobe here, which is really following uh, A. It is really following A, except its value is very close to 0. Of course, we have to discuss why this is happening. We have not come here. We are trying to make sense of the different terms. Diffusion constant of B is much higher. Now, there are two things we could do. What happens if we change beta? If we change this difference, which was, so this beta is 1. Now, if I change this, right? Because presence of A actually would increase the presence of beta. This del B del T equal to uh, B, I mean, diffusion term plus beta into A minus B. Now let's see what would happen. So I compile, I presume, yes, beta equal to 10. Now, if I do domains, so you get a different pattern. Okay, okay. So you have these two small lobes here. You have a right angle lobe here, another lobe like this, and so on. Okay, now if I add another figure and do domains B, I hope this is figure 2. Yeah, this is figure 2. The difference has increased. Something else, these lobes are still there, this 90 degree, this one, this, and we can compare figure 2 with figure 1 here. So here you can see they look very similar, but the values of b, the variation in the values of b is much closer to 0, whereas here the range is more green somewhere here to 0. Okay. Uh, Now one can go on changing the diffusion constant, the value of alpha, the value of beta. Now I'll just play a bit with the value of alpha just to see what happens. It's 0.05. Now if I did 0.005, what would happen? Okay. And also I want to change the range, c-axis range to say -1 to +1 for domains A, and also similarly for domains B. Right? And if I compile, I think what I'll do is keep this to be 0.5. Let's see whether there are some negative numbers which appear. So let me compile again and run it. Okay. So here the maximum range was 0. Now I have put in negative range as well. So, so just 1 second. Ah, it seems much more interesting. The range has changed. I think the color range, you still get these two different patterns, but values now actually vary from +1 to -1. Okay. And I guess that's something similar which is going to happen if I had figure 2 figure, and then I did domains P. So we can get all these different patterns, but what is happening? That's the question. I mean, figuring out itself is a bit difficult, I guess, but I've read up what's the mechanics, what's the phenomena that is happening, uh, right? And here you see that you have some negative numbers and some positive numbers. So B is also varying from some positive numbers in the pink domain and some negative numbers. So there's a density variation in the lattice of for B as well. Of course, these follow the densities of A, but the yeah, right. So this is what you're getting now. No, okay. So now, suppose I changed the diffusion constant of B. B is not diffusing as much, right? And did the entire calculation identically. Uh, so I suppose compile. run. So here all that I changed is the diffusion constant of B, right? And once it has completed the run, what I can do is plot. Oh, it became a stable solution. And I wonder why. Oh, okay. Another reason. Because I see this B here, beta is this, but now if I change alpha and run it, then I got a, now we have negative numbers. I see. And if you plot it, again you are getting lack of patterns. Uh, oh, there could be another reason for this. Maybe the range is too much. Just let's check. Yes, I had played around with this also in the past. And suppose you do 0.5 to 0.5. Maybe then you see patterns appearing because the density variation is too less. Uh, yeah, maybe. So you see, there's a lot of scope for playing around, and I haven't even touched the initial conditions. I could also start from when all numbers are positive, or we start from numbers which are greater than 1, right? You have some quite some amount of uh, room to play around. Uh, I'm recording. Uh, well, here again it gets all stable. I see. So let's look at the file data. They seem to be truly uniform all over. So it has somehow reached a perfectly stable fixed point, and that was only because I changed the value of diffusion constant from 100 to 10. So this original criteria where diffusion constant of B has to be significantly greater so that those product of the sums basically these conditions. I think in one of those when I've changed the value of diffusion constant, no. Uh, Somehow I think this criteria is not being satisfied, this third one. Hence we are getting all uniform densities. Now if I increase this to not 100 but say 50, okay, so I have not explicitly checked the number when that gets mm, mm, okay. Now what does one get? You saw that it's yes. Again, we started getting patterns. I think that criteria got uh, dissatisfied. So we are getting stable fixed points. And here you see there are variations from +1 to deep blue, which would be something like minus zero point 0.5. So we have this entire gradient, and you have these pink regions which have this value, and so on and so forth. Okay, so we have played around a bit, and there's endless scope to play around, which you can do on your own, and maybe add some noise terms as well, change diffusion constant of A, and so on and so forth. And so let me tell you what is basically happening. Now, what is happening is A is trying to increase, wherever there's an excess of A is trying to increase the value of A, of course. Okay. And if there's a perturbation, and that leads that leads also to an increase in the value of B, because del B del T is diffusion term which tries to diffuse away local high concentrations of A and B and tries to make it uniform. But there is also beta A minus B. So if A increases, locally B increases. Now increase of B suppresses the concentrations of A and B, right? But wherever A has increased due to a local fluctuation, A has increased, B also follows, but then B is extremely quickly diffused away. It is spread away over large distances. So here you have a concentration increase in concentration of A somewhere, where it is driving the value of A up till it reaches some stable point. But at other points, the values of B dominate over A, and pulls it down. It pulls it down because B has diffused away. So wherever there are lower values of A there, the B gets dominant and pulls it down uh, to negative values, right? Because it basically takes it away to another stable point locally in the lattice. So because of this competition between uh, where A is trying to increase concentration of both A and B, B is trying to decrease, inhibit. It's an inhibitor. It tries to inhibit the concentration of A and B. But wherever B is following A in an increase, B is also spread away very quickly away to other regions where B is pulling down the values of A and B both. So this is the reason why you are starting to get patterns. So that's a physical intuitive, my attempt to give an intuitive understanding, and under what conditions you will get patterns and not get patterns, of course, can be. I've briefly summarized it in these lectures, but to have a better understanding, you should, of course, go to Pushpavanam lectures. But then, if you add noise, I think you can get spiral patterns, you can have different values. So, at the moment, we have beta A minus B. You can introduce another parameter beta 1A minus beta 2B, so that you can play around further. There's endless things that you can do with this, playing around with parameters and seeing. At some point, while playing around and preparing for the lectures, I had also managed to get some spherical droplets, right? So I won't record that, but I'll try to play around and tell for what parameters you can get. Well, you are already starting to get droplets here, right? Rather than stripes. There are quite a few droplets, and all that I did is decrease the diffusion constant of B from 100 to 50. Maybe if I get do it to 40, maybe I'll get droplets. I'll just try out, and then I'll stop the recording because I'm just curious. Now, suppose I go to 40. Remember, if you increase B, then you have to take care of dt also. But if I just do 40 and run it, Yeah, you start getting droplets, fewer droplets. These are circular patterns that you have started getting. So these are called, I think, cheetah stripes, and those stripes are called zebra stripes. And I mean, there's an enormous amount of literature just on Turing patterns. And these are just to concentration. Then you can also have coupled equations with stress, strain, uh, other variables. I mean, it's extremely rich field. I mean, just playing around with partial differential equations. Here we did a minus a cube, but you can also do a minus a square, right? And even the inhibitor, we have minus beta. You can make it that also nonlinear. So I don't know what those equations are called, but there's huge scope. And what I would be interested in, not as part of the course, is how to create the spiral patterns. I just saw yesterday you have to add some noise, but just adding some noise, I guess, is not going to be enough. There's some other stuff to be done. Anyway, so I've shown you how you can play around with these parameters, and of course you can change the range of c axis, axis. You can change the initial conditions. You can start with a so here we are initializing the entire lattice with +1 -1 and so on and so forth. Now what do you do? Now, what would you have if you had just a small patch in the middle of the box? So suppose you initialize everything to 0, but when we talk about linear stability analysis, we talk about a small deviation. But of course, when we discussed it, we didn't have the diffusive term. We didn't have the x and x dependence, x and y dependence of a and b. Uh, but now you have that x and y dependence of a and b over and above the Fitzhugh Nagumo terms. And what you could also do is start with where all the lattice points are suppose 0, or say zero point 0.5 or 1, but only a small patch uh, where you put a perturbation, you put it a non-zero value. So if you have that perturbation and the center, say, does it increase, decrease, does it go to stable points, how would it evolve? So there's a huge scope for playing around. There's no point in recording all of it. You can play around on your own whenever you have time. But anyway, what we learned is basically a cheap way, a simple way, explicit finite differences method to solve time dependent partial differential equations. And this is a starting point for a huge field, as I told. And of course, you have these better, more stable methods as well. Those you need to solve those large number of simultaneous differential equation, and solving simultaneous differential equation using the matrix method you will be learning in the Prashanjit last module of the course. Yeah, so we use the most simplest one, which is easy to code and yet get some interesting stripes and cheetah spots. Hopefully you had some fun with this. I shall stop sharing first of all and stop recording.